Hello and welcome to Jules Bench. My name is Greg Perugini and this lab is on oscillations. Now we've studied before in the previous semester on Hooke's law and springs and how they oscillate. Well, we talk a little bit more about oscillations in this semester. Sound and light travel in waves defined by wave properties of frequency, wavelength, and period. Now we can simulate this spring action with an elastic string. In your kit you have some elastic string and a metal ring that we'll use to create an oscillation. So we must pull this down from equilibrium. So you have this elastic string and you have a ring. And so you're going to pull this down a distance and measure that distance. So that's, in a sense, that distance from this point to this point is your amplitude. Now you want to let go of this and you're going to time it for 2 oscillations. How long it takes to do 1, 2. And then when you do that, you'll have, and you divide it by 2 and you'll have the period. But we'll get to that in a little bit. That restoring force is based on Hooke's law. So you see what's going to happen. We pull it down, we let it go, it goes up, comes back down. It will go back and forth, up and down, in a sinusoidal motion, repeating itself. The period is the time it takes to go from this point to this point. The distance between those 2 points is a wavelength from crest to crest or trowel to trowel, either way. Now, if you notice when I did that experiment, you found that it's going to slow down. Of course, with friction and in the air, it's going to actually slow down to a stop. But if there were no friction and no energy lost, it would keep going like that forever, right? So this is an example of simple harmonic motion. So the amplitude is that amount of distance that I pulled down, and we do this twice, right? From the time from this point to back to this point twice and divide by 2. And that's going to give you the period of the oscillation. With that, we could plug in and create the equation for our string system using this standard model for simple harmonic motion. A is that amplitude that I mentioned, and the period is 2 pi, make sure you put parentheses around that. Some calculators don't handle that correctly unless you do, divided by omega rads per second. So I get the period by the timing that we did, and you could use an app for stopwatch or whatever way to try to time as accurately as you can. So you take that time, 2 pi divided by that time will give you the omega, which you can plug in here and plug in your amplitude, and you will have your equation for your system. Now this matches simple harmonic motion. This here is the phase change, the phase constant, and we're going to just consider that 0 for now, because we're starting with no velocity. We're going to assume that we're also starting at a cosine. So, in conclusion, we're going to calculate the period, 2 oscillations, pulling it down, having it go back to that point again, and divide by 2. Repeat that for 5 times so you could get a good average for your period. You use that period to calculate your rads per second. Of course, you measured your amplitude to figure out how far the stretch is. for your particular system, for your particular action you did with a simple harmonic motion, and you've created an equation for your system. So that equation, you should be able to predict the position of the ring at any given time, again assuming no friction. For your prediction, of course, make sure you're in rad mode, because inside the cosine is rads per second squared, so you need to be in rad mode. So that's the lab that you'll be doing.